Hi, my name is Rose, and my presentation is a story about processing very large data sets using Apache Spark clusters in the cloud. So this story starts where I thought that I was a software developer working with data, and over time, as working with data came to occupy a larger and larger proportion of my daily life, I realized that I was a data engineer at the wrong end of the pipeline, which is a really bad place to be. It led to a situation I like to call resting batch face. Really bad. So I decided to change something about my life and move to the front of the pipeline where you can fix problems before they grow intractable. So that's how I moved to working with data full-time at Coatue Management. Coatue handle a number of large, distinctive, interesting data sets. But they share one unifying factor: horrible skew. Also undesirable input formats. So here is kind of a representative data set. It's about 35 terabytes raw, 80,000 files, unsplittable compression, row-based. It has skew so terrible that I can't even think of a metric invented to portray skew like this. And it's got a deeply nested directory structure. So basically it has been designed so that ingesting this with Spark is as difficult as possible. And once you do have it ingested, now you've got to consider how are you going to put it all into memory at once, because that is a processing requirement. And also, you've got computationally heavy stages that require caching this data set. So I actually tallied it up, and over the course of a successful run of this pipeline, more than 275 billion rows of data are cached to disk. Finally, what are you going to do with the results? You have to get those off a transient cloud cluster somehow. So we have stages where tens of terabytes of data are written back out to S3. How are you going to process that? And you've got a very big Spark cluster, but that's the start, not the end, not the answer. So the more nodes that you have, the more important tuning Spark becomes. Everything, memory management, network communications. And on top of that, where are you going to run that? Because a lot of Spark jobs or presentations about Spark jobs you read about where they're processing huge amounts of data, they're running in a data center, but data centers aren't a magic solution. Really, if you consider it, a Spark cluster is not an island. It exists in a whole ecosystem of supporting services, and infrastructure management is really hard. And optimizing Spark jobs is hard. So running in the cloud has some big disadvantages. You've got I/O variance, you've got unreliable nodes, but the truth is, if you can find a way to live with that, then you can leverage the infrastructure of management that the cloud offers to run really big jobs. And, but on the way, what I would like to say is a lot of experimentation is going to be required. And because you deserve it, there will be screenshots of things going wrong at scale. All kinds of things going wrong at scale. Because, you know, a lot of configurations are not meant for such large clusters. A lot of things need to be tuned. And let's be honest, sometimes you see a presentation and you see configurations and you think, wow, that looks really great. This will solve all of my problems. And because who does not love the delight of the unexpected? You put it into your cluster and fire up 1,000 nodes to see what will happen. Well, I took some screenshots. It's going to be awesome. You'll love it. No configuration exists without surrounding context. Even really great presentations require surrounding context. So let's talk about, when you're in the cloud, what are your options for putting together a so-called big Spark cluster? Are you going to use big instances, small instances, medium-sized instances? What are your resource constraints for the executors? How much memory? How many cores? Now, one answer that would be really great would be just the most enormous node that you can imagine with a whole bunch of executors. And this is great because you don't have big shuffle overhead, great data locality. The downside is that, like a pony, your data center does not, your cloud provider does not offer this instance type. Also, very poor fault tolerance. So moving on, you've got kind of the compromise, multiple medium-sized nodes, and now you have a choice of stacking stacking up multiple executors on a single node or individual executors, which may not be the best resource usage, but you know, ultimately it's your job and you have to decide whether over-provisioning represents a good use of resources or not. Now, the most important question here is, what is the impact to my job if I lose a node, losing n executors? And because this is the cloud, you also have to think everyone else wants the conveniently sized node types as well. So how are you going to provision as many of these nodes as you need? Finally, the worst of all solutions, a whole bunch of really small nodes. These are inconvenient node sizes. They're not really big enough for multiple executors, but they're kind of too big for a single one, so you're over-provisioning. On the other hand, it's really fault tolerant. This is the single most risk-averse strategy. The impact to the job of losing one executor, or even 10 of them, is pretty much nil, because an executor is a single node. So on the other hand, it has big communication overhead. It's expensive, and also provisioning, depending on your cloud provider, may be kind of difficult because, you know, you can't always just spin up 1,000 nodes when you want them. So why would you ever choose the worst solution? Well, if your cloud provider is acting up, this is the one. It's resilient to degradation and loss. It probably is the closest emulation to the kind of over-provisioning you get when people develop code in notebooks. And finally, it offers you a way to make use of the awkwardly sized instance types that nobody else wants. So onward. Now that you have some idea of what you might want your big cluster to look like, now we can talk about what you're going to need to do to tune memory management, communications, job scheduling, and talk about, well, once you've got data on the cluster, where are you going to cache it, and how are you going to get that data off the cluster? So memory, probably right off the bat, your biggest consideration, because the first thing that's going to happen is you're going to ingest all that data, allocation's going to go through the roof, and you're going to see some kind of GC type event happening. So what does memory look like on your Spark cluster? Now, assuming just parallel GC, it's going to look a lot like this, okay? Just out of box, you've got a third of the space allocated to the young generation, and 2/3 to tenured space, and then you've got Spark memory fraction controls kind of the working space for execution. Half of that by default is execution, half storage, although the proportions are dynamic, and then you have like 40% for Spark metadata, out of memory, safety, whatever, 300 meg reserved. So that's kind of what it's going to look like to start with. Now, how do you know that you have a problem? Really easy. When you go to the Executors tab in Spark UI, and it looks like that. The red part means it's spending more than 10% of its time on garbage collection, which really adds up. So, field guide to Spark GC tuning. If you see lots of minor GC, there's an easy fix. Give it more Eden space. Now, anyone who's really familiar with GC tuning is going to know that there is no technical distinction between major and full GC. We're talking in terms of impact, frequency and impact. And hashtag goals, your goal is to get through each stage without a full GC. And what you need to do that is to understand what is your trigger for these frequent major GC events. So is it promotion? Give it more Eden space. Is it old gen filling up? Then either decrease the amount of working space or increase the old generation size. In general, your tactic is to trigger smaller, minor GC events more often. So, and now Worst case, everything is wrong. The quickest thing to do is throw money at it. More or bigger nodes. If you already did that, then you have to go into the code. I love it when people say, look for avoidable shuffle. It's really easy to say that about other people's jobs, you know, but yeah, you're gonna have to really, maybe the cheapest fix is to try to checkpoint at strategic points. This destroys lineage, but maybe that's a positive thing. So also make sure that you're only caching to disk, and you can try, if you're not pressed for CPU, you can try compressing data in memory. The ugliest thing to do is really get under the hood with joins. Finally, which garbage collector? Let's be honest, if you're spending 10% of your time on CPU, try the other one. If you have very wide rows, avoid G1, GC. Otherwise, try using that with 35% for initiating heap occupancy, because again, you want to trigger minor GCs early and often. Parallel GC figures throughput, and it's really kind of a natural choice, but there's no reason why G1, GC can't work for you as well. Now, these big data sets, where are you going to put them? And the answer is to disk, which is slow, but way faster than restarting and recovering a Spark cluster which just died because it was out of memory. So you need to keep as much of the old generation free for Spark execution space as possible. So this screenshot shows a 20.3 terabyte data set cached all on disk, nothing in memory. So it totally is possible, but there's something very big that you've got to be aware of. Namely, what happens if an executor dies? And the answer is you just lost all the cached blocks stored by that executor, even if the node is still running. This really happened. That was so bad. So when the executor dies, two things can happen, both of which are bad. If the lineage is gone, the job fails. If the lineage is still there, it's going to try to go all the way back to the source files and regenerate, which can really slow your job down if your ingestion is ugly. So how can you, good news though, a configuration exists which can solve this, proactively replicate. Also, if you are using a non-distributed file system, if you are not on HDFS or some other distributed file system, make sure to use replication of greater than or equal to 2. Not that I would ever have done anything so stupid as to have used cache to disk with a replication of only 1. So next up, networking. This is so important because this is the backbone of communications. RPC, go look at transport conf, because this is the shared config for both shuffle and authentication. And to be honest, not all of the configs in it are really either documented or explained in the Spark config docs. So if RPC is not given sufficient resources, essentially your cluster will slowly drift apart and just die. So first off, you need to increase the size of thread pools. Now this here is a linear scaling factor that you can use as a rule of thumb for scaling up your thread pool. So the default is 1, which is ridiculous, all right? You need to start with 2, and then maybe consider going all the way up to 8. I've never gone up past 8, but if you do and it works, email me. Now this presentation was given by Facebook at Spark Summit in San Francisco year before last, tuning Apache Spark for large-scale workloads. This is pretty much the definitive presentation on tuning shuffle for large data sets. So I'm not going to repeat it here, but remember when I said that no configuration exists in isolation. What you've got to understand here is that you can't just pick up these settings and drop them onto your cluster and expect them to work as great as they do for Facebook. So I'm going to talk here about some things that weren't presented in that configuration, in that presentation, or which are different. So first off, you need to consider when you have 500 to 1,000 shuffle clients, what are the interactions between the client and the server really going to be? And over time, we arrived at this strategy, namely to scale the shuffle server way up, increase all of the resources. So index cache size, 256 meg. Hey, if you're running one of those many small nodes clusters, give it a gig. It depends how many blocks you have, what's the size, how many shuffle partitions do you have, okay? Because you need to scale the cache size based on the number of shuffle partitions that you have. So also the backlog, hey, the sky's the limit. 8192 is a great number. And keep in mind, the RPC lookup timeout is not adjusted by Spark Network timeout. So bring it up here if you need to. And so while scaling the server up, bring the clients down, throttle them, make the clients more patient, more fault tolerant. The clients need to just back off and wait if something goes wrong. So when you have a config like this, I like to say you are conceding resources and speed in exchange for stability. This is what a higher P50 in exchange for a more predictable P99 looks like. So, and what we found was that so far, this config has not been knocked down in production. As Run DMC says, the turntables might wobble, but they don't fall down. So also, finally, how many connections does each peer get to the server? 1, unless you have a lot of executors stacked up on the node. Otherwise, 1. All right, number of shuffle partitions. This is so important. Now, at Spark Summit in San Francisco this year, Daniel Tomez gave just a seminal presentation, Apache Spark Core Deep Dive Proper Optimization. This presentation was a blockbuster, and if you haven't seen it yet, you absolutely have to go watch it. But one of the suggestions that he made was that for each input, for large shuffles, you should take the max shuffle stage input and divide by 200 meg, which, let me do the math here, is 5242 partitions per terabyte. Now multiply that by 35 terabytes. Wow, that is a lot of partitions. It's probably more shuffle partitions than you have ever run Spark with before. And so, of course, naturally, in the spirit of experimentation, I tried that. It was amazing. I have never seen a join run that fast, right up until the point where the wheels came off the race car and the cluster went up and it went up in flames. It RPC'd itself to death. I would have taken screenshots, but I think I was crying. It was bad. It was bad. I was looking in different log files, tailing different log files, thinking, can it make it? Can it make it? No, it can't. Everything fell apart. So, and here's a big lesson: highly aggressive shuffle optimization is required for this recommendation to work on a large cluster with a lot of nodes. That is all. So remember, scale the server up, scale the clients down. Otherwise, really good stuff. Now, kill spill. The #1 cause of terrible performance on a very large Spark cluster is spill. This setting controls when and how Spark spills data from memory to disk, which is something that in practice, if you have enough memory, you don't want to happen. And the defaults are a terrible choice. So you want to set this, so having cleared off so much memory by doing such an inconvenient thing and persisting all of your data sets, caching all of your data sets to disk, now is the time to go spend it. Make this number as big as you can. All right, scaling S3 writes, getting data off of the cluster. Okay, what you've got to consider here is the S3 support in Hadoop 3.2.0 is so awesome. Unfortunately, your cloud provider is probably going to be using a version of Hadoop from the Middle Ages. So our recommendations briefly are for EMR, that EMRFS did not work out for us, and that you should write to HDFS and then copy off using S3 disk CP while limiting the number of reducers. And that for Databricks, writing to S3 just works. Good stuff. Now, scheduling. This, more than anything else, is a story of unintended consequences, unexpected side effects, because Spark Scheduler is so powerful, but there are so many little knobs, there are so many unintended interactions. So I'd like to tell you some things that we didn't necessarily expect would happen, that some configurations that worked great on smaller clusters or on different cloud providers, but when we really scaled up, caused strange things to happen. So, just to mention dynamic resource allocation, you may have heard of it. If you run transient clusters in the cloud, this will do nothing for you because it's intended for co-tenants. However, external shuffle service, that's the point you should take away from dynamic resource allocation. And what is that? External shuffle service is intended to keep those shuffle blocks alive even if the executor goes away. In theory, external shuffle service should be more responsive than the node itself, although in practice, in a large cluster, you're gonna have to tune those settings to make that actually happen. So, yeah. So speculative execution. So this can be kind of a great safety margin. When you have tasks that for whatever reason are running pretty slowly, what Spark does is at a certain point, it's going to take your slowest running tasks and relaunch them because on the natural assumption that they're running slowly because there's a transient problem with the node that the executor is on, which is great. That's usually what's happened. However, sometimes that's not the real story. What if the estimate for the tasks, for the time the task takes to run, is bad? What can cause the estimate for the time the tasks take to run to be bad? Skew. This presentation could almost have been titled, "Every Way in Which Skew Can Ruin Your Life." But yeah, you got to deal with skew up front. So these here were our default speculative execution settings, and they worked great, you know, because the estimate for the median task size at 80% of the task being done was good. But all right, here is a screenshot showing 21.2 terabyte shuffle with 20% of the tasks killed. And just so you're sure, that there is Ganglia showing 86 tasks active on a 1,000 node cluster. A sight I hope never to see again. Not good. So what happened here is that due to horrible skew, Spark took the slowest, longest running tasks and launched duplicates, creating what I call a snail race, where essentially the cluster just sits there idle while the remaining executors sit there chugging away on the slowest running tasks. So the solution was kind of twofold. To first kind of increase the speculation quantile so that it starts later, maybe gets a better estimate, just bump up the speculation multiplier, just start speculating a lot later, but also do something about the skew, you know? And I don't want you to get the wrong idea. Speculative execution is actually a great tool for a large cluster. It probably was not intended as such by its designers, but it gives you a great margin of safety because when a task that would have failed anyway, counting as a failure for that stage, adding up to the maximum number of failures that stage can support, is killed by speculative execution, that doesn't count against you. Great. So, you know, also it's a canary in the coal mine. When you see speculative execution killing a bunch of tasks, that's a sign for you to go in and investigate what is going on. Pro tip, it's usually skew. So, all right, blacklisting. Blacklisting is kind of another escape valve for scheduling. What it's meant to do is to take a node that is having problems for whatever reason, just out of the rotation. And it's highly configurable, maybe even too configurable for its own good. But what it's doing is, kind of removing tasks that would, removing an executor where tasks would fail anyway from rotation. Now, what is this? Oh my gosh, this is a 1,000-node cluster where 892 of the executors have been blacklisted. What happened here? We were writing 3 very large data sets to S3 and 17 terabytes in. We got 8,600 errors writing to S3 in the space of 8 minutes distributed across 1,000 nodes. So some executors back off and retry, succeed. Speculative execution kicks in and keeps some of them alive for a little bit longer, but all of the nodes quickly accumulate at least 2 failed tasks, and many more get blacklisted, eventually translating to 4 failed tasks, killing the entire job. And here, sorry, I think I was panicking. This isn't the greatest screenshot, but what you see here is essentially all of the executors which are not yet blacklisted are about to get blacklisted. So, wow, that is not what I wanted to happen. So don't blacklist too soon. So the postmortem, remember, everything looks obvious in retrospect from a good postmortem, but we needed to be more, we needed to back off on our blacklisting, but as well, our S3A cluster size was not big enough. So we needed to raise our multi-part upload size. Who could have thought with 17 terabytes of data to upload, we might need to do that. But also we needed to make blacklisting more tolerant of failure. So, and finally, task reaping. So what the task reaper does is reclaim failures when reclaim resources when your executor gets wodged. For some reason, it's just sitting there spinning, it's not coming back. Kill it and reclaim the resources. So, however, the one thing is, obviously, you would like the proactive block replication that you've turned on to work. So give the task reaper a bit of time before it just kills that executor. Now, finally, tuning. In general, you cannot go wrong by increasing timeouts, buffers, thresholds, just raise that. And if you are running MapReduce style stages or tasks, consider how many reducers do you have in your cluster? And is the thing that is being hit by that reduce step expect to be hit by so many reducers? If the answer is no, you need to decrease the number of reducers. And let's just talk about network timeouts. A very large Spark cluster is more prone to network timeouts than smaller Spark clusters. So this is the biggest knob you can turn. And as I wanted to warn you, it does not configure shuffle or authentication timeouts, but it configures just about everything else. Last, executor heartbeat timeouts. This looks like a networking problem, but it almost certainly is not. It is almost certainly a resource problem, a memory issue. So what you need to do here is go back, and it's probably skew. The answer to almost every problem on executors is almost probably skew. So, and then finally, let no task, just accept some level of failure higher than you would probably like, especially when you're dealing with external services. Just try again, keep trying. You know, the default is 4. How about 10? What about 12? Keep going. It is better to concede some amount of resources and duplicate efforts than it is to have the whole job fail because you let it fail after only 8 attempts instead of 12, or something like that. The magic number of failures differs by cloud provider, but in general, you know, very few people are going to say, why did you accept 12 failures instead of why did this job fail because you didn't accept enough failure? So, I mean, you should absolutely look at why you're getting so many failures, but give yourself a safety margin here because you can. So, Finally, I would like to remind you that as frustrating as it can be to be on the pointy end of a Spark job which is not working, a Spark job that is not working is only a special case of a Spark job that is working. It can happen. So, all right. Again, my name is Rose. I work at Coatue. We work with large data sets in the cloud. If you are interested, email me, or I'm at Prasinus on Twitter, and I will now take questions.
Thank you, Rose, for the wonderful session. Hope everyone enjoyed. This is for the Q&A. If you have any questions, come to the mic area.
Oh, I'm so sorry. I could not hear your question.
No, we're getting the questions. Just a second. I'm a track moderator.
Oh, yes,
yeah,
there.
Just helping you.
All right.
First of all, I want to thank you for such a nice presentation. It was really helpful. So I have two questions. One question is, when you were referring to blacklisting, were you using Yarn scheduler, or it was Yarn resource manager, or you were using Spark standalone?
We were using the Spark scheduler.
Okay, standalone.
Yes.
Okay, second question is, like, could you please recommend some tools for monitoring, debugging apart from Spark UI that would be helpful to us to actually find out these kind of issues?
Well, to be honest with you, there's a bit of a gap in the market. What I do is I use Spark UI and Ganglia, and then I go back. I use the Executors tab on Spark UI, and then I go back in the logs, and I just download all of the logs, and I correlate times in the logs against the driver file and the various Executor files, and I just have a lot of log files open back and forth, and then I go back into the Spark source code. And of course, I take a ton of screenshots. Now, one thing that Databricks does that I really love, and I'm not saying this just because they organize their conference, is they take historical screenshots of Ganglia, which is like a flight recorder. It is absolutely crucial if you're trying to understand. In a long-running Spark job, if you don't have a Grafana, a Graphite, like something set up in collecting the Ganglia metrics, then sometimes you don't know what resource usage looked like at a certain point in the job. So I only wish that somebody would make a tool that screen scrapes Spark UI at every point in the job. That would be great. So there are some automated tools I am aware of, such as Unravel, but I mean, I don't really know. I wish I knew of a good one. I would recommend it to you.
Okay, great, thank you. I have one more question. Like, could you please recommend some metric which will be helpful to us to look into Grafana, like the Spark metric, which are really important in terms of tuning?
Well, the first thing I would look at is just too much GC and spill. Spill is, if you're spilling, if you see, just grep the logs for the word spill. If you see the word spill, fix that.
All right. Thank you.
Yeah.
Thank you for the presentation. It was great. What's your take on doing the Spark joins when you are dealing with such massive volumes of data, and what sort of programming changes that you actually made on your code level to make the joins work properly, and what's your experience? It would be great if you could share that.
What was the first part of your question?
It's about what sort of programming configuration changes that you made on while doing the Spark joins with massive volumes of data, like how you did with terabytes.
Okay, so, so the question was, what programming changes do you make to support large joins? And I would say the number one change for supporting very large joins is to be aware of skew. To try to turn skew into like a broadcast join if possible. Remember when I said leave a lot of memory on the table, because that will facilitate a broadcast join, even a very large broadcast join when you need to do one. Also making sure different cloud providers with different Spark implementations have slightly different Catalyst SQL under the hood. So for instance, Databricks has some optimizations which are not available on EMR. You'll find joins perform differently on every cloud provider, to be honest with you. But just really get in under the hood and look at the query plans in great detail. Look for anywhere where you see red in the query planner or just a large number of rows. Anywhere where you see that the query planner expects way more rows coming out than are actually coming out. That's indicative of the query planner maybe not understanding what's going on. There are some great deep dives into the Catalyst SQL query planner in previous years of Spark Summit that I found extremely helpful myself. So.
And also, there's one more question. So would you recommend running multiple Spark jobs on a single cluster in case if there is a requirement, or it's always sequential execution is preferred?
Would I recommend running multiple Spark jobs? The answer would be personally no, because it leads to non-deterministic performance. Coatue tend to run single-purpose transient clusters in the cloud because we are processing relatively large data sets with which arrive, we need to get things done in time for trading. We have time limits. So if we had no time limits and co-located hardware in a data center, I would probably give you a different answer. But, with the setup that we have now, I couldn't recommend it. And the same goes for scheduling stages in parallel, even on a single purpose cluster. It may seem like a more efficient use of resources, but the truth is it makes it very difficult to debug performance because it's non-deterministic.
Any preferred scheduler that you would use?
Honestly, I have experimented around with scheduling, but the truth is scheduling was very rarely the problem with my job. I'll put it to you that way. The problem was ingesting skewed data, poor join strategies, just not configuring shuffle appropriately, spilling to disk. Scheduling was never the problem for me. So.
Thank you.
Thank you. So. All right. Hi. Yes. Well, we are a small team, so like original sin, we all share the code. So I actually probably spend less time working on the code than many of my colleagues because I'm often working on development tools or configuring Spark jobs, but we all share the code. Everybody, all postmortems are blameless. We all share the code. So the only interest of a postmortem is to reveal what the problem was and how we can fix it, how we can better detect it in the future. So just to be constructive. So nobody, ownership of code is entirely collective. So there's no fault. There's only an opportunity to learn how to do better, and who doesn't want to do that? So. You can't take mistakes personally. So, well, so I'd like to thank you all so much for attending, and also to say that I have about 30 slides worth of configurations, detailed memory tuning, and information which did not make it into this presentation, which will be available online if you are interested for later perusal. So also some detailed S3 configs, just all kinds of interesting stuff, plus links to good presentations, blog articles, just good stuff in general. So I hope that you will go and look for my slides online later. Or you can find me here. I have a printout. So thank you all so much, because I've probably learned something from those of you in the audience. So, you know, we are but dwarves standing on the shoulders of giants. So thank you all.